Okay, thanks, Serene. For those of you who were at Rome last week, you're excused. I'm going to give essentially the same talk. So if you don't want to hear it again, then please feel free to leave. So this talk is supposed to be a perfect illustration of the Bob Powers theory of research. So I want to remind you about that. He may not be responsible for this theory, but I learned it from him. So so I call it the Powers theory of research. And here's the idea: you have the researcher here who has a bow and an arrow. I guess the arrow is like this. Okay, and you fire off the arrow. And it lands. So this is the definition of research. And now comes the research part. You simply see where it's landed, and then you draw a target around there. So this, as I said, this talk will be in large part an illustration of this theory in practice. Okay, so what the talk is actually about is an attempt to produce some kind of conformal field theory associated to any subfactor. Most of you probably know that there's been a wealth of discoveries of new subfactors of finite depth, partly as a result of this classification program for small index subfactors. And there doesn't seem to be any major reason why they couldn't come from conformal field theories. Of course, we're all waiting on Terry Gannon, who's supposed to be producing a vertex operator algebra related to the Hausdorff subfactor, but well, it's a sort of he's always 2 weeks away from it, so. Anyway, this is a completely different approach, and the lesson today will be that this approach just doesn't work. It's a total failure. I mean, works about as badly as you could possibly imagine. And that's what I want to talk about today. But then I apply the Bob Powers definition, and I say, well, you know, it doesn't work, but maybe we should do something else. The mathematics will be very interesting, and maybe we should do something else. So I want to begin the talk by reminding some of you and explaining to others a nice little chapter in mathematical physics. If you like, it's the easy part of the Baxter F solvable model program, the quantum inverse scattering method. And it's very pretty, and if you've never seen it before, you will be delighted, and if you have, then you'll be delighted also because it's nice to go through it again. I'm going to use a bit of notation for tensors, for manipulating tensors. And the idea will be that we're going to have a tensor. A tensor is always going to be represented by something with legs. The legs will have the indices I, J, K, and L. And if we want to say what tensor we're talking about, we'll put the tensor sitting in there. So this is supposed to, this notation is supposed to mean a tensor with 4 indices, I, J, K, and L. Right? And the rule for manipulating these is simply that this is very well known, very standard convention. When you draw a picture involving lots of tensors, you simply contract over all indices that are not on the boundary. So, for instance, if we had R here and S here, then this diagram here would simply represent the contraction over these two indices. So you'd have Ri something L, R, J something K, and obviously what we recognize here is the sort of matrix multiplication of tensors. If we think of this tensor as being a homomorphism from the space tensor power here to this tensor square here. This is just composition of homomorphisms, so very standard. Now the tensor that I want to form right away is the so-called transfer matrix. So our indices here, you can think of them, if you like, in the simplest instance as being spins, so a spin up and a spin down, but we might have higher spins or higher values for the indices. The main case I'm going to be using is when the indices go from 1 to 3. So the transfer matrix is the following. So there's a certain number of edges here. There's a given tensor R, which I'm going to put in. Well, actually, for convenience, I'm going to have R, which is going to be family indexed by one parameter. So one parameter family of tensors like this. And instead of putting R of lambda, I'm just going to put lambda. Okay, so this picture here represents a tensor, which basically the guts of it goes from I1, I2, I3, I4, In, whatever n is, to J1, J2, J3, J4, J5. And it's basically the homomorphism, the linear map from this tensor space here to this one, but then there's these extra indices, which I guess I should if you don't like those extra indices, then you can easily just impose what's called periodic boundary conditions, and that just means, according to our convention, these indices are no longer on the boundary, so you sum over them. So we make them equal, of course, and sum over them. So that's some kind of partial trace or conditional expectation or whatever you want to call it. So we're sort of probably going to do this. So this matrix here with the periodic boundary conditions is called T of lambda. Okay. Does anyone have a question about this notation? If you wanted to write it out in full, you would put indices here, 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 and you take the product of the corresponding R's and then multiply the corresponding R's and sum over all of these indices. Very standard convention. So you get a sort of complicated looking matrix whose entries are products of sums of products of the underlying this thing called the R-matrix. So perhaps the main use of this transfer matrix is actually in two-dimensional classical statistical mechanics, where you build up the lattice with periodic boundary conditions. You build up a lattice simply by applying this, you would just take T lambda to some power K, capital K, right? This would mean just stacking this diagram on top of it, and you see the lattice forming before your eyes. And something like the trace of this thing, it would be the partition function of some classical statistical mechanical system where the Boltzmann weights are given by R. Okay? It's also, as we'll see, comes in more directly in what we're concerned with, which is a one-dimensional system of so-called quantum spin chain. We'll see how that happens in a second. Okay, so this is the transfer matrix. Now, the beginning of the miracles is what happens if the R matrix satisfies the so-called Yang-Baxter equation. Now see if Sven did this so brilliantly. The water is in the bucket somewhere? It's in the sink. All right, let's see. I don't have the boots, unfortunately. No. How do you do that? Gotta get one of these at Bodega Bay. All right, so the Yang-Baxter equation. So it's an equation, it's a sort of small equation. So this operator, the transfer matrix, is kind of a big operator, right? So acting on a, if you let the number of indices at the bottom be big, then it's quite a big matrix. Yang-Baxter equation is a small equation on the individual matrix R of lambda, and it says the following. It says the following. We're going to put, as I said, I dropped the R, so we're going to have a lambda there and a mu there. And the equation says that there's another value which we can call lambda plus mu, and it's equal to. All right, so I want to put it on the right-hand side. These crossings, this crossing here is between this string and this string, so that lines up with this one here, and this is mu. And then lambda is there, and lambda plus mu is in here. So it would have been much smarter to put it over here. Oh, no. Anyway, doesn't matter. The thing to note about this equation is simply that the mu and the lambda have got swapped around. Okay, mu has gone down to the bottom, and lambda plus mu has gone from here over to here. Okay? Now, as I said, this is a diagram in tensors, right? So our convention is we put the indices all the way around the outside, same indices around the outside, and we sum over these things. So it's a cubic equation, right? Product of 3 lambdas, 3 r's equals a product of 3 r's. Okay? If you write it all out in actual terms, it's a highly overdetermined system of cubic equations, but it has some solutions. All right, now, what we're going to do is look at the consequences of the Yang-Baxter equation on our transfer matrix. Okay? So this is a small equation. It's just local, involves 3 r's. But what it's going to imply is a fabulous relation between the transfer matrices themselves. And this is how it goes. I'm going to have the transfer matrix T of lambda, and this I'm going to implicitly employ the periodic boundary condition. So this actually goes around like that. And then I'm going to take T of lambda, T of mu. So there's T of lambda. Oops. And here's T of mu. I compose them. Remember, composing is just stacking. And now here's the trick. This is the cunning Baxter strategy here. What we're going to do is I'm going to add T of lambda plus mu here to the picture. So I'm going to multiply now in this horizontal direction by T of lambda plus mu. And then here I'm going to put T of lambda plus mu inverse. The inverse being for the multiplication that way, for the composition that way. Okay, you may say, well, why does it exist? Well, all things are generic. I suppose it exists. All right, now, the magic. Here we have T of lambda, whoops, I didn't mean to put T, just lambda plus mu. Here we have lambda plus mu, lambda, and mu. And if I draw in all the things in their correct places, which I surely haven't, don't worry too much about that, this one will come past this one and flip the lambda and the mu. So the next step, this will be equal to, so it'll be mu, lambda, mu, lambda, mu, lambda. And then there'll be this lambda plus mu. And then this will be mu, this will be lambda, and this will be mu. Because that's what the Yang-Baxter equation does. It flips lambda and mu. Okay? And then this is inverse going. Okay? Everyone saw that happen? But now now we just simply continue to push this across. This lambda plus mu now goes past this one. It flips lambda and mu. And it keeps on going until it gets to the end of the chain, at which point all of the mu's have gone down there and all of the lambdas have gone up there. But then, periodic boundary conditions. This actually comes around the back, and what does it see? It's inverse. So it disappears, it cancels out. We introduced it and then it cancels. So we get at the end of the day that this is equal to lambda, lambda. Okay, so we get this commutation relation, T of lambda mu equals T of mu to T of lambda, which is a wonderful thing. Okay. It means that at least completely rigorously, it means that they have the T of lambdas and have a single common eigenvector which doesn't depend on lambda. Okay. Now the physicists will immediately say, well, there's an orthonormal basis of eigenvectors and so on. And then the work starts. So this is the easy part, and one might say the rigorous part. Okay? The next stuff has assumptions about existence of eigenvectors, linear independence, and so on, to actually get the so-called beta-Ansatz equations coming out. But I'm not going to talk about them. I just wanted to, as I said, explain this and then explain the relevance for quantum spin chains. Here we go again, boys. Right. I wish I had those boots that Sven had. That's very good. Well. Okay, so that's the underlying rather beautiful piece of mathematics. Now, the physics, we're going to think of the quantum spin chain. It's simply going to be the Hilbert space C squared tensor C squared tensor. Where the number 2 here is really just some integer. It could be C3 or it could be C to the K. But, you know, we think of spin up, spin down as the nicest case. But I'm going to apply it, as I said, when 2 is equal to 3. So this is the Hilbert space of a chain of spins that are sitting right next to each other they're constrained to sit that way. Now, so what I'm going to do is I'm going to make a hypothesis on R. I'm going to suppose that R of 0 is equal to this thing here. Remember, R was this guy here. Right. So, and what I'm going to do, so this is part of the quantum inverse scattering game, is I'm going to take the logarithmic derivative. So first of all, let me just take the derivative of R of lambda and put lambda equal to 0. See what happens. There's going to be another piece of magic comes out of this. So let's do this. So R of lambda is this guy. I'm sick of writing all of these lambdas. All right, so we want to take, T of lambda. T of lambda is this guy, and I want to take T prime at 0. So what is it? Well, we have this fabulous product rule for differentiation, right? It says you differentiate with respect to 1 and so on. So this is the sum. So we differentiate this one and we get R at 0, R prime at 0, which we put in here. Right? So we've hit this one with the derivative, and who knows what this is, R prime of 0. But then we put in 0 for the other values. We know what happens at 0. It's the hypothesis. It's R of 0. So that becomes this guy. Right, things have got rotated, so that's this hypothesis, because this one and all of the others are the same. Okay, so it's a sum of these. First of all, we differentiate with respect to this and this and this. And then we take the logarithmic derivative, which means we divide by T of 0. So 1 over T of 0. We've got a well, we just invert it, which just means putting this back. Okay? So what we get at the end of the day is the sum of things where we have right. This picture gets rotated back to me. Okay, so we get, in other words, I'm just doing this stupid differentiation, right? But what it comes out is a sum of terms where there's something happening between I and I plus 1 and nothing happening anywhere else. Things just go straight through. So what's that? Well, that is the perfect candidate for a two-particle interaction Hamiltonian. Okay, this is something happening between I and I plus 1, a nearest neighbor interaction summed over all of the nearest neighbors. So this guy here is your candidate Hamiltonian. All right. So besides this Yang-Baxter business, if we have this condition and this condition alone, let's never use Yang-Baxter, we have these candidate Hamiltonians. Throwing that together with the Yang-Baxter equation, we have not only a Hamiltonian, but since we worked in this T of lambda the entire time, everything is going to commute. So we have this Hamiltonian has this big family T of lambda of commuting matrices. Okay, so if we can diagonalize the T of lambdas, we have actually also diagonalized the Hamiltonian, and we can get the eigenvectors and eigenvalues for the Hamiltonian from our this matrix trick, the T of lambda trick. Okay, so this is the other part. This is sort of more the Faddeev part of the quantum inverse scattering method. We get a family, every time we have one of these nice solutions of the Yang-Baxter equation, we get a family, we get a Hamiltonian, which in principle, whose spectrum in principle we can calculate. Okay? It's the in principle that's the hard part, right? This is all the easy part. The in principle part is you start to make hypotheses about the vectors and linear independence and so on. But I'm just going to stick to the easy part today. Okay. Any questions about that? So the reason that I did it in such detail is that that's what that I'm going to do some things, and you really wouldn't have much of a clue about what I'm doing unless you know that little chapter. But in any case, it's a beautiful little chapter from mathematical physics. My technique is not very good, is it? Well, get there. Okay, so now I'm going to switch to another little bit of more physics-related stuff, which I'm not going to say very much, but because I'm going to be taking it as motivation for another thing, and that's the so-called Ketonoff Wilson block spin renormalization. So here, once again, the idea goes back to sort of 2D or 3D, perhaps more interesting even than 3 and even 4D, models like this, where the idea is that we're interested in what's happening at criticality, so some kind of criticality, and the great philosophy coming from up there is that at criticality, things exhibit some kind of scale invariance. So if you take a picture, you can actually, I did this actually, simulate an easing model on your computer, get to the critical point, and you'll see that the pattern of spin up, spin downs, if you zoom in, just looks the same at criticality, and it doesn't away from criticality. So the idea is that in order to analyze this mathematically, possibly, hopefully, you can implement scale invariance by taking a block of spins, so maybe 9 spins, and then replacing them by a single spin on a much coarser lattice. And then you would look for interactions such that the Hamiltonian or the Boltzmann weights, the partition function, is invariant under this transformation, or at least maybe it scales with a factor under this transformation. If you find that, then you have a system which has some kind of, you should be able to isolate the critical point by looking for fixed points under this renormalization transformation. All right. I want to think about the same thing. I'm not alone in having done this on a quantum spin chain, where we have these spins sitting at various lattice points. And the Ketonoff Wilson philosophy would say block a few together to make a spin chain on a coarser spin chain. So let's just imagine the simplest case of blocking these two spins together, these two spins together, and these two spins together. That becomes a single spin here. And then we look for Hamiltonians or transformations or whatever that are invariant under this change scale. If we can find them, then that should have something to do with criticality. One dimension, yeah. You can criticize that, right? Because it's not really the same thing as this one in 2 dimensions applied here. But let's give it a shot, see what happens. As I said, Power's definition of research is applying in full force. Okay, so now what I'm actually going to do is I'm going to invert that procedure. And the motivation for that comes from, as I said, from this subfactor business. What I want to do is I want to start with a subfactor or whatever data that gives and try to construct a theory on an infinite dimensional Hilbert space and hopefully some kind of conformal field theory. Now, conformal field theories come in these 2 chiral halves. Okay, so they're supposed to be theories on the circle where you have the Hilbert space and the symmetries of the circle come into play. In particular, there's supposed to be a action of the diffeomorphism group, unitary representation on the Hilbert space of the circle. And then there's supposed to be these local algebras in the spirit of Haig-Kastler as local algebras on the circle. Now, you see, the point is, and this is going back to the motivation, I won't dwell on it because I want to get somewhere. What a subfactor gives you in spades is, for each time you have a circle and you have n points on it, you get a Hilbert space. Okay? You get a Hilbert space for a circle with n points on it, and if you have n points and m points, they're related. That's what subfactor theory is all about. So the naive idea was to just try to let these points on the circle become dense and obtain the conformal field theory as some kind of limit as the points become denser and denser on the circle. That's a nice sound thing, right? Any physicist would like that idea. But now I'm going to convince you that it just doesn't work. It really doesn't work. So anyway, the relevance to this renormalization is somehow you've got to take n points on the circle, add some points, and get a bigger Hilbert space. So you're embedding the spin chain with n points in the spin chain with n plus 1, or why not double each time? Spin chain with 2 to the n points and 2 to the n plus 1 points, and so on. So you've got to be able to do that. Well, you know, if you take this block spin renormalization, that sort of says, well, just do that in reverse, right? So instead of blocking the spins together, you're going to unblock them. So you're going to take this quantum spin chain where maybe there's 2 to the n spins here, and then you're going to use this, whatever it was, this fork here, to embed this spin chain. This will be the tensor product 2 to the n times of c squared or c cubed or whatever, inside the tensor product 2 to the n times of n plus 1 times. All right? Now we want to be in Hilbert space, so we want this to be an isometry, and the isometry condition is on this guy, and it's this. This has to be equal to 1. So what I want to explore now, and that's just mathematically, is this going to work? And I want to convince you that no, it really isn't going to work. Okay. And then we go back to Bob Powers and say, well, let's do something. Let's take it, take what it's given us, and make it work in some different way. All right. So. What's next? So the basic ingredient, the first ingredient is going to be what do we use as this fork? Remember, this fork was just in the block spin. It was some transformation which went from C2 tends to C2 to C2, and we're taking it as going the other way. So a priori, with nothing to guide us, we could have anything there satisfying this condition, and maybe everything would depend on that. So to narrow down our choice, we're fortunate to have a nice paper by Morrison-Peters-Snyder, one of whom is here. And they have this nice paper which analyzes, the simplest instances, let's just say the simplest instances where you can have this kind of gadget. Okay, they do a complete analysis and they list all of the examples. And we're going to take from that the simplest of their examples, which is basically, for those of you who know quantum groups, it's SO3Q. I think. I don't know quantum groups, so I'm just spouting this. Anyway, if we work in this SO3Q, which means that the whole spin chain has some kind of quantum group SO3Q invariance, then there is a unique choice of this guy. So let's work with that. Okay, that ties down this freedom. So I'm going to show that it really doesn't work in this case. Okay, and in this case, there's no choice about this guy, so really, it's just not working. All right, so what's not working? What's not working? Well, as I said, what we're trying to get is on this limit Hilbert space. The limit Hilbert space exists, right? These are isometries, and you can compose them, and you get one Hilbert space inside the next one, isometric inclusions, and we all know how to take the inductive limit of that. You just take the vector space limit and then put the inner product. These are all isometries, complete it to get a Hilbert space. So that's supposed to be the continuum Hilbert space for the circle. Okay? And whatever else conformal field theory says, you can go different ways. The rotation group is supposed to act. Okay, that's the L, and the infinitesimal generator up to some things you might quibble about is supposed to be the L0, the theory. So the very first thing we inspect is a nice continuous one-parameter unitary representation of the circle as the limit of these circle representations. So, the circle, you can just rotate the spins. Okay? So what I'm going to show now, I'm going to do the calculation for you. It's kind of cute, and it will lead to different things. But I'm going to do the calculation which shows that rotation by smaller and smaller amounts is about as discontinuous as it can possibly be. And as Alice pointed out to me, it's like white noise. So we're going to get some kind of quantum white noise coming out of this thing. All right, so the calculation. So let's do it. This really is kind of fun. So I think what we have to do, we have to take a vector. So what we've got, obviously what we want to calculate is this kind of thing. Rotation by 1/2 to the n of some vector with itself or another vector. Okay, so we're rotating a tiny little bit, and we want to take that in a product. And we want to show that that, of course, tends to get continuity, that would have to tend to psi eta. So we're going to do the calculation of that quantity and show that it doesn't tend to psi eta. So we're really stuffed. I see you can't cheat. This is like making coffee, You can't cheat in the water. If you don't put the right amount of water in, it doesn't work. So next time I better wet this. So let's just do this computation. All right. So what do we have to do? So psi and eta are some vectors. So they're sort of, some originating vectors here. Some vector in this Hilbert space with a bunch of spins. But we want to look at the case, we want to let n tend to infinity, right? So if psi starts in some kind of, say 2 to the 5 dimensional space, we want n to be 1,000, then what do we have to do this? In order to apply the rotation by 1 over 2 to the 1,000, which is pretty small, we have to embed it up a whole bunch of times. We have to consider this vector here in a much finer Hilbert space, but we know how to do that. It's very simple. Actually, I want to draw this picture fairly carefully. Not my style, but this time we have to. So let's take this vector and embed it up. So we've embedded up on one finer scale, and we embed it up again. So imagine this picture going on and on, and this is just a picture of psi. Psi is down here somewhere, sitting at some scale. And we've embedded it up to sit at that scale. Right? Now, in this game, how do you take inner products? Well, to take inner products, you just reflect things and take the adjoint. I think Arthur's going to tell us a much better way to do this later on in the day. So you reflect things and take the adjoint. So we want to take eta. It's going to sit up the top in this little thing, and it also is going to get embedded up. So sitting here, we'll have this, we'll have this, we'll have this, we'll have this, and these two will again bifurcate. And then you join them, you take the star of this. This has got to be some complex conjugate or something. Maybe you reorder the legs. Okay, so if we wanted to take the inner product of psi with eta, this would be the picture. We'd just join these up. But we have to rotate it by one small unit. So this is what happens. Instead of joining them up like this, we join them up like this. And this is the picture I want everyone to stare at for a while. Because I've been preparing you all for this. You may not realize it. But here it is. I think that what I want to do is I have to do this the right way. I'm going to isolate that guy, and then I'm going to isolate. So look hard at this because I'm not going to baby you through it. I'll just assert that it is what it is. So on. So what you see here is this pattern here is repeated here and here and here. And what's joining them is this thing here. That one joins this brown one to this brown. That one joins that one. And that one will join the next one, and this one joins the next one. So after a little, redrawing of the picture, what we get is this. Okay, where inside these circles, I simply see this picture here. Okay, so we can redraw that as inside one of these, I've got, someone can tell me if I'm wrong, I've got that. So this guy here gets inserted in all of these. Okay. So now I'm going to suggestively call this guy lambda. Right, and what do I see here? I see nothing but the transfer matrix with lambda in it. All right. But now you can see what happens. when I apply this to this, this thing here, this has 4 boundary points. So when I apply that, I get a transformation. I get another value of lambda. I get a lambda by applying this transformation to lambda and lambda. I get some new lambda, this renormalized lambda. Okay. Must have the wood. So think about that. What's happening? I've changed scales. And I've simply changed parameters in the transfer matrix. So thus, if I define this renormalization transformation as follows, renormalization of lambda to be so this has taken a value of lambda and produced another one, so this is renormalization of lambda. Then all I'm doing in calculating this thing is remember that this is just part of the picture. There's there's squillions. If n was large, there's squillions of more steps of this. So I'm just taking the iterate. So I'm just taking Rn of lambda. And as n goes to infinity, at the end of the day, I'll get down to the original vectors, which are in the vector spaces, and the inner product will be sitting there for us. Okay? But what is this? What is this transformation? This is simply, you write this out. This is in some basis. This is simply a value of lambda times the value of lambda equals something or other. This is a dynamical system in the classical sense, which is quadratic, right? If we had, if lambda were in some basis sigma bi ci, then this would be, the renormalization would be something like ci cj, whatever. So it's a quadratic. It's just simply a quadratic renormalization. Now, of course, because of that, if you start iterating it, because it's quadratic, if you're close enough to 0, you're going to get closer and closer and closer to 0. All right? So the only thing you have to check is that with this starting point, that one there, that I drew, that lambda there, as endpoint, I iterate this renormalization transformation and check that that tends to 0. You have to be careful there because, it's a quadratic system, not a linear system, it's a quadratic system. So it has its, points can go off to infinity. There's a Julius set and a Mandelbrot and all of that sort of stuff is there. You have to be careful. But I have been careful, at least my computer has been careful, and I've been able to show that in all cases, except some exceptions, which are even worse for some other reasons, where you don't actually go to 0, you get in this attracting zone around 0 and it goes to 0. Okay? Now, once all of these lambdas are going to 0, it's a fairly simple game in annular. It's contained, there's some result contained in the paper of Shami and Corey, but it was so deeply buried in there that I had to reprove it, so not very hard. Which shows you that the actual norm of this transfer matrix, which is an annual thing, the norm of the transfer matrix actually goes to 0 also. And so this, in the product, I didn't say what the result was. Rho 1 over 2 to the n psi eta tends to 0. Okay? So it's, it's completely uncorrelated. The smaller and smaller a rotation you do, the less correlation is between the two things. I should perhaps say, maybe I shouldn't say this, but I can't help it. I've been puzzling recently. This is all very well to show rho 1 over 2 to the n psi eta goes to 0. Does that mean that the limit of the rotation as the rotation tends to 0 is also 0. I'm not sure about that. I've made it go to 0 by taking this particular value 1 over 2 to the n. Right? And the calculation worked because I only rotated by one little thing. If I rotated by a whole lot of clicks, then the situation is more complicated. And I haven't proven, it may even not be true, that this rotation, this thing tends to 0. But anyway, absolutely no hope of the thing being continuous. So this is a no-go sign. You do not go this way. But we're all disobedient people by nature, so we're going to go that way anyway. And we're going to take from this, we're going to say, all right, what's the lesson here? The lesson is that the infinitesimal value behavior of the rotation is determined by the transfer matrix. And it's the same transfer matrix that I was talking about before. The infinitesimal behavior of the rotation is determined by the transfer matrix. Now we go back to that classical picture, that quantum inverse scattering picture. What was, remember in conformal field theory, there's only one space and time, so the rotation is actually time evolution. And the generator of time evolution is the Hamiltonian. And the Hamiltonian was given, remember, by the logarithmic derivative of the transfer matrix. So in the usual picture, the infinitesimal behavior of infinitesimal correlation is determined by the transfer matrix. Same thing. Okay, so we've got this sort of topsy-turvy world where that statement is true in both of them. The infinitesimal behavior of the rotation is determined by the transfer matrix in both pictures. So we say, oh, maybe we should take this seriously and examine some more consequences of this. And unfortunately, I've talked myself into very little time to do this, but this is where it starts to get fun. Another reason for doing it is to say, well, it's all very well what I haven't introduced any dynamics right in this picture. All I've said is how to block the spins, and that's a kinematic thing. So before giving up completely, I should investigate the possibilities of having a Hamiltonian, or a transfer matrix, at least. So in the few minutes that remain, I'm going to tell you a little bit about the possibilities of a scale invariant transfer matrix. All right? So if we had a transfer matrix that was scale invariant, then we would want this picture here to be equal to this picture here. In order for that to happen, it's obviously sufficient to have this local equation, sort of analogous, if you like, to the Yang-Baxter equation, that this is equal to this. Okay, because if you have this equal to this, then you just string them together and you have scale invariant transfer matrix. Now I cheated mightily by not putting in the values of the so-called spectral parameter here, because what you find is when you try to solve this equation, you find that there are no solutions with spatial homogeneity. In other words, well, there is one, it's the so-called braid solution, but if you want to have a lambda in here, you cannot have lambda equal to lambda. You have to have lambda mu, okay, and some third one, lambda mu and gamma here. Okay, so the lesson is, if you want a scale invariant transfer matrix, it's not going to be spatially homogeneous. But hey, let's give it a go anyway. Let's try and solve this equation. Now this is not too bad as equations go. As I said, this is sort of quadratic and this is linear. So you're just solving a system of quadratic equations, which are not too bad. And if you were Japanese or something, you could surely do it by hand. If you're me, you would actually need to use Mathematica, and then at the end of the day, you would go back and say, well, I could have done that by hand. Anyway, I've done it. At least Mathematica has done it. And I've got what I think is the general solution. And here a miracle occurs. So let me remind you, we're solving this equation. And the solution is given lambda, okay, so given lambda, in this model, there exists a unique choice of mu and gamma such that this equation holds. Okay? This is different from the Yang-Baxter equation. The Yang-Baxter equation said, given lambda and mu, there is a lambda plus mu such that the Yang-Baxter equation holds. So when you just give yourself gamma, the others are unique. Okay? Now, so being out of time, I'm going to skip this. So, what's the miracle? Miracle is, the solutions of this equation, lambda, are on the Yang-Baxter curve. In other words, if I give myself two of these, lambda and mu, which may have nothing to do with this diagram, they certainly don't get put in the same picture. There is a third one, lambda plus mu, such that Yang-Baxter holds. Okay? Now, I would think this was a real miracle if I hadn't already done a whole lot of other calculations where Yang-Baxter was already somehow implicit. But I cannot say that I understand this at all. Okay? This system of quadratic equations, relatively simple, produces a solution of the cubic equations of the Yang-Baxter equation. All right, so I need to wrap it up fairly quickly. There's sort of problems that come up along the way. This, by the way, the actual solution that you get is one of the very early models in the coming out of the Leningrad, St. Petersburg group. It's the Izergin-Korepin model, solvable model. And as I said, it was one of the earliest ones discovered after what we call the Temple Leap thing today. So anyway, just a few words on how it goes. There's actual problems. If you give yourself, if you want to construct this, the idea is to construct this scale invariant transfer matrix on the limit, okay? And lots of things go wrong. The first thing that goes wrong is if you have your transfer matrix here, then you're forced to choose lambda and mu on the next scale. So who's to say that this lambda will also be the source of another one? Well, that goes right. It is, provided the parameters, there's some bad values of the parameters. At the end of the day, you certainly want a nice fat interval of lambdas with which to work, but you can prove that there's a nice interval of gammas, an open set in the complex plane, for which this process can be iterated and produces for you some values, some t of lambda, with lambda in some open set or an interval of the reals. Another miracle. So remember, don't forget, we're now going to have the transfer matrix is going to be spatially non-homogeneous. Spatially horribly non-homogeneous, these things are going to have all this sort of Cantor-type behavior. And a priori, you could not expect the transfer matrices to commute, right? That argument that we had with the, where we flipped them over, that relied heavily on the lambdas being the same everywhere. But by a miracle, another miracle, it so happens that the transfer matrices, mu1, mu2, and so on, they still commute. That same argument works. In other words, when you start passing, if you put arbitrary things in here, when you started passing that thing, trying to pass it along the chain, it would get stuck. But the way it works out, the mathematics works out, it doesn't get stuck. It goes all the way around, and you get commuting transfer matrices. So, that's the really good news. So there's a common eigenvector and so on. So the pieces of bad news are there's one value that really doesn't want to be taken in this picture, right? Really doesn't want to be taken, and it's lambda equals 0. Okay, so that means that there's no chance of a local Hamiltonian by the same thing. And the other piece of bad news, and these are all part of the package that you would expect because it doesn't work, T of lambda, the thing on the inductive limit space, what do we call it, the semicontinuous limit, does not go to the Hilbert space. It's an unbounded operator with no domain in its star, as far as I can tell. So maybe the inner product's wrong. Maybe we need this reflection positivity that Ada's going to tell us about this afternoon. So anyway, I'm 5 minutes over time, so let me stop there. Thank you. This is a very good question, you know. So I didn't even tell you what we do, drawing the target around. So let me say a few words about that. You know, right, we don't get conformal field theory, but we get quantum spin chains with scale invariant transfer matrices. For goodness sake, maybe that's as good or even better than conformal field theory. And you know, so I always put you this question: imagine you have a spin chain, macroscopic spin chain. How many spins are there in it? About 10 to the 8th, right? This 10 to the 8th, right? It's not 10 to the 23rd, it's 10 to the 8th. It's the cube root of 10 to the 23rd. So you look at it, and you can almost see those very grainy. You can see those atoms or molecules there. So what's a better model for that? The continuum or this sort of p-adic structure? Interesting question. So let's go ahead and investigate this p-adic structure. The group of symmetries of the whole thing, instead of being the diffeomorphism group, will be the Thompson group. And that's what led me into this, which is by definition scale, local scale transformations, local scaling transformations. So maybe you can get some stuff out of the Thompson group, some critical exponents and so on. And the most obvious one, someone's right on the ball, is how fast does that go to 0? Now this is a simple problem, right? This is just simply a classical dynamical system, quadratic dynamical system. You can write it down completely explicitly. Just look up the paper by Morrison-Peters-Snyder. It gives you all the coefficients of your dynamical system, and you say, how does this go to 0? As in terms of, was it logarithmic, is it exponential, so on and so forth. So I did some calculations and so on, and I was having a bit of trouble, so I asked the experts. I asked Jean-Pierre Ekman in particular, who was one of the founders, and after a reasonably long exchange, the answer was, we don't know how to do that. Which, my response was, what are you guys doing if you can't do that in this simple dynamical system? But, he didn't try all that hard, I'm sure, with a little bit more work. And that question will be answered, I'm sure. But, that's the kind of thing, you get some numbers, which may have something to do with critical exponents, and so we have a critical system, or scale invariant system. So that's a very good question.